Our view of the cosmos is a tiny bubble in an unimaginable ocean. We are about to take a journey to the absolute edge of reality, exploring 30 of the most profound mysteries the universe has to offer. You will come away with a completely new perspective on everything from the cosmic horizon to the staggering possibility of a multiverse. We will confront what might lie beyond our sight and question if our universe is truly alone. Which single cosmic question keeps you up at night, staring at the stars? Our cosmic horizon is not a physical wall in space, but a frontier in time. This first great mystery is the limit of everything we can ever possibly see. We call this boundary the cosmological horizon, and it marks the edge of our observable universe. It exists because the universe has a finite age, around 13.8 billion years old, and light travels at a finite, though incredibly fast, speed. This creates a fundamental limit. We can only see objects whose light has had enough time to travel across the cosmos and finally reach our telescopes. Every time you look at a distant star, you are looking back in time, seeing it not as it is now, but as it was when that ancient light began its journey. The most distant galaxies we observe appear to us as they were just a few 100 million years after the Big Bang. This means our entire view of the cosmos is a series of historical snapshots, layered one on top of the other. Picture yourself standing in the center of a vast, dark sphere. The inner surface of that sphere is your cosmological horizon. Every point of light you see, from the nearby moon to the most faraway quasar, is painted onto that inner surface. The mind-bending truth is that every observer in the universe, on any planet, sits at the exact center of their own, uniquely tailored observable sphere. There is no universal center, yet we are all at the center of our own cosmic perspective. So when we talk about the edge, we are really talking about the ultimate limit of our information, a horizon defined by the finite speed of light and the age of the cosmos. That horizon we just explored, the limit of our vision, is perhaps the most profound boundary in all of science. It is a border that defines everything we know, but it raises an even deeper mystery. What lies beyond it? What exists in the vast cosmic territories whose light has not yet, and may never, reach our eyes? We are confined to our island of visibility, forever wondering about the nature of the ocean that surrounds it. The most accepted scientific theory suggests the universe is infinite, stretching on forever in every direction. If that is true, then beyond our cosmic horizon is simply more of what we see here. More galaxies, more stars, more planets, continuing without end. The idea is almost impossible to fully absorb. Our minds are built to understand objects with edges, like a book or a building, but the concept of a reality that truly has no edge, no boundary whatsoever, is a staggering mental leap. Think of a vast, endless forest. You are standing in a small clearing, and the light from your lantern only reaches so far in the trees. That circle of light is your observable universe. You can see the trees within that circle, but you know the forest itself continues on, mile after mile, into an unimaginable distance. The trees beyond your light are still there. They are real, but they are hidden from your direct perception. This leads to a humbling philosophical truth. If the universe is indeed infinite, then the part we can see is less than a single grain of sand on an endless beach. The totality of everything that exists, the complete cosmos, is fundamentally and forever unknowable to us. We are trapped within our tiny bubble of spacetime, able to theorize about the outside, but never able to visit, never able to see. So we are left with a haunting question. Are we on a cosmic island, isolated and alone, Or are we simply one small clearing in an infinite, eternal, and endless forest of reality? This notion of an infinite cosmos hinges on a single fundamental property, the actual shape of the universe itself. This is our third great mystery, a question of geometry on the grandest possible scale. What is the overall form of all that exists? Scientists have narrowed the possibilities down to three primary shapes, each with staggering implications for the ultimate fate of everything. The first possibility is that the universe is flat. In a flat universe, the rules of geometry we learned in school, Euclidean geometry, hold true on the largest scales. Parallel lines will never meet, and the interior angles of a triangle always add up to exactly 180 degrees. A flat geometry strongly suggests an infinite universe, one that simply continues, unchanging and endless, in all directions. The second shape is spherical, like the surface of a balloon. This is a positively curved or closed universe. On a sphere, parallel lines eventually converge, and the angles of a triangle add up to more than 180 degrees. A spherical universe would be finite, but just like the surface of a planet, it would have no edge. If you traveled in one direction for long enough, you would eventually return to your starting point from the opposite direction. The third possibility is a hyperbolic shape, often compared to a saddle or a potato chip. This is a negatively curved or open universe. Here, parallel lines diverge away from each other, and the angles of a triangle add up to less than 180 degrees. This type of universe would also be infinite and expanding forever, but in a dramatically different way. To probe this cosmic geometry, scientists use the oldest light in existence, the cosmic microwave background. This faint afterglow from the Big Bang is a snapshot of the infant universe, and it is imprinted with tiny temperature fluctuations, like a fingerprint of the cosmos's initial conditions. By meticulously measuring the size and pattern of these hot and cold spots, we can deduce the universe's shape. If the spots appear a certain expected size, the universe is flat. If they appear larger, it suggests a spherical, closed geometry. If they appear smaller, it points toward a hyperbolic, open shape. The astonishing result from satellites like Planck is that the measurements align almost perfectly with a flat universe. The data tells us that on the largest scales we can measure, the cosmos appears geometrically flat. This finding is one of the strongest pieces of evidence we have for a potentially infinite reality. Yet this answer is not the end of the mystery, but a gateway to an even deeper one. If the universe is flat and infinite, what could have set it on this specific, precise geometric path from the very first moment of its existence? That flat geometry of the universe is a clue of incredible significance, pointing directly back to the very first moments of existence. To explain this perfect flatness, and to solve other profound puzzles, cosmologists have proposed a truly spectacular event. They call it cosmic inflation, a period of exponential expansion that occurred in the first fraction of a second after the Big Bang. This was not the steady, stately expansion we see today, but a violent, faster-than-light stretching of the fabric of space itself. The universe doubled in size, then doubled again and again, in intervals so brief they are almost impossible to describe. In less than a millionth of a trillionth of a trillionth of a second, a subatomic speck of reality was blown up to a size larger than our entire observable universe. This idea solves one of the most stubborn problems in cosmology, known as the horizon problem. When we look at the cosmic microwave background in opposite directions in the sky, those regions have the same temperature, to an astonishing degree of precision. This should be impossible. According to the standard Big Bang model, those two regions were never close enough to exchange heat and equalize their temperature. It would be like two people on opposite sides of a vast ocean spontaneously deciding to wear the exact same outfit without ever having communicated. Inflation provides the answer. It proposes that these distant regions were indeed in close contact in that infinitesimal first moment, before inflation violently pushed them apart, locking in that uniform temperature across the sky. It also perfectly explains the flatness. Think of the surface of a balloon. When it is small and deflated, its surface is highly curved and wrinkled. But as you inflate it to an enormous size, any tiny patch of that surface appears perfectly flat to an ant crawling on it. Inflation did the same thing to the cosmos, stretching any initial curvature so thin that our entire observable universe appears geometrically flat. Yet for all its explanatory power, inflation is one of the greatest modern mysteries. We do not know what triggered this phenomenal outburst of energy. The leading theory involves a mysterious field, called the inflaton field, which possessed a peculiar property. It was trapped in a high-energy state, like a ball perched at the very top of a hill, and its energy caused space to repulse itself, driving the exponential expansion. Then, for reasons unknown, the field decayed, rolling down that hill and releasing its immense energy in a firestorm that filled the universe with the hot plasma of the conventional Big Bang. But what was the nature of this inflaton field? What kind of hill was it sitting on? And what was the final push that sent it tumbling? The mechanism that started inflation and the precise reason it stopped remain completely unknown. They are puzzles buried in the very first instance of time, pointing to a physics we have not yet discovered. This uniformity of temperature across the cosmos presents a classic and deeply puzzling mystery in its own right. Why does the universe look the same in every direction? When we observe the cosmic microwave background, the ancient light from the early universe, we find its temperature is almost perfectly even, no matter which part of the sky we point our telescopes toward. Two regions on opposite sides of the observable universe have precisely the same temperature to within a tiny fraction of a degree. This seems like it should be impossible. According to the standard Big Bang model without inflation, these two regions were never close enough to exchange energy or information. They are separated by a distance so vast that light, even traveling for the entire age of the universe, has not had enough time to cross from one to the other. They exist beyond each other's cosmic horizons, forever out of touch. So how did they manage to coordinate their temperature with such incredible precision? It is as if two people living in completely isolated towns, with no phones, no mail, and no contact of any kind, both decided to set their thermostats to exactly 72.1 degrees. The odds of that happening by pure chance are astronomically small. This is the essence of the horizon problem, a paradox that challenged our understanding of the early cosmos for decades. The leading solution, as we touched on, is cosmic inflation. This theory proposes that in the first sliver of a second, the entire observable universe was compressed into a tiny subatomic region that was in perfect thermal contact. It was all one cozy, uniform room. Then inflation acted, stretching this tiny, connected patch into a volume larger than our entire visible cosmos today. The regions that were once neighbors were violently wrenched apart, carrying their identical temperature with them across the sky, even though they are now forever separated. While inflation elegantly solves this puzzle, the precise mechanism that drove this hyper-expansion remains one of the most active and contentious frontiers of cosmology. We do not know what the inflattened field truly was, or why it started its roll down the energy hill. Different models propose different types of hills and valleys for this field, leading to different versions of our cosmic story. The debate continues, centered on an event so brief it defies measurement, yet one that set the stage for everything we see. That perfect uniformity of the early cosmos set the stage for everything to come, but it also points toward a final, chilling destination. The ultimate fate of the universe is not written in the past, but in the behavior of a mysterious force we are only beginning to understand. Dark energy, the enigmatic driver of the cosmos's accelerating expansion, holds the key to how our grand story will end. The leading scenario, based on our current best measurements, is known as the Big Freeze or heat death. In this future, dark energy continues to push galaxies apart at an ever-increasing rate. Over trillions of years, the stars will burn through their fuel and wink out, one by one. Galaxy clusters will become isolated islands, drifting in an ever-widening void. Eventually, no new stars will be born, as the raw materials for star formation are locked away in dead stellar remnants and cold, diffuse gas. The universe will grow progressively colder and darker. The last light in the cosmos will fade, leaving behind a sparse sea of black holes, cooling stellar cinders, and lonely planets. Even these remnants will not last forever. Over almost unimaginable timescales, black holes will slowly evaporate through a process called Hawking radiation, and protons themselves may decay. The final state would be a universe that is utterly dark, uniformly cold, and essentially empty, a thin soup of fundamental particles separated by astronomical distances. This is the heat death, the ultimate triumph of entropy where all energy is evenly distributed and no work can ever be done again. But is this our only possible destiny? Other theoretical endings are far more violent. One is the Big Crunch, a dramatic reversal of the expansion. In this scenario, the density of matter and energy in the universe would eventually overcome the push of dark energy, causing the expansion to slow, halt, and then reverse. Galaxies would begin rushing back toward each other, the cosmos heating up as it collapses. The universe would end in a fiery inverse of the Big Bang, all matter and energy compressed into a single point of infinite density. Another possibility is the Big Rip. This occurs if dark energy is not constant, but grows stronger over time. In this terrifying finale, the repulsive force would eventually overcome all other forces in nature. First, it would tear apart galaxy clusters, then individual galaxies. As the end nears, stars would be ripped from their solar systems. In the final moments, planets would be shredded, and then atoms and atomic nuclei themselves would be torn apart. The fabric of spacetime would be ripped to pieces. The choice between these fates rests entirely on the precise nature of dark energy, a force that makes up about 70% of the universe's energy budget, yet whose identity remains one of the greatest puzzles in physics. Is it a constant form of energy inherent to space itself, leading to the long, slow freeze? Or is it a dynamic field that can change, potentially dooming the cosmos to a violent rip? Our distant descendants, if any survive that long, will witness the final chapters of this cosmic story, living in a universe growing steadily more lonely and dark with every passing eon. The nature of dark energy is arguably the most profound puzzle in all of modern science. This mysterious force, making up about 70% of the entire cosmos, is not just some minor component. It is the dominant player, the engine driving the universe's accelerating expansion. Its discovery in the late 1990s was a complete shock to astronomers. By observing distant supernovae, they found that the universe is not merely expanding, but that the expansion is speeding up. It is as if you tossed a ball into the air, expecting it to slow down and fall back, only to watch it fly faster and faster toward the sky. Something is actively working against gravity's pull, pushing galaxies apart with ever-increasing vigor. That something is what we call dark energy. So what could it possibly be? The leading and simplest idea is the cosmological constant. This concept, first proposed by Albert Einstein and later abandoned by him, suggests that empty space itself possesses a fundamental intrinsic energy. According to quantum physics, the vacuum of space is not truly empty. It is a seething, bubbling foam of virtual particles popping in and out of existence. This quantum activity could endow every cubic centimeter of space with a tiny, constant energy that produces a repulsive gravitational effect. If this is correct, dark energy is a permanent and unchanging feature of the cosmos, woven into the very fabric of reality. The universe would then continue on its current path toward the long, cold Big Freeze. However, there is a major problem. When physicists calculate the predicted strength of this vacuum energy, the result is a number that is wrong by a factor of 1 followed by 120 zeros. It is the most infamous and embarrassing discrepancy in the history of physics. This colossal failure has led scientists to explore a more dynamic alternative known as quintessence. Imagine quintessence not as a constant, but as a new cosmic fluid that permeates all of space. Unlike the cosmological constant, this energy field could change over time. It could weaken or strengthen, its repulsive power evolving as the universe ages. The name quintessence comes from the ancient idea of a fifth element, a substance beyond earth, air, fire, and water that permeates the heavenly realms. If dark energy is quintessence, the ultimate fate of the universe becomes wildly uncertain. Its acceleration could continue forever, it could slow down, or it could even reverse and become attractive, potentially leading to a cataclysmic big crunch. The true identity of dark energy is not just an academic curiosity. It is the key that unlocks the final chapter of our cosmic story. Will our universe end in ice, or in fire, or in a violent tear? The answer is written in the nature of this mysterious, dominant force that we cannot see and do not understand. While dark energy pushes the cosmos apart, another invisible force holds it together. The mystery of dark matter is a story of missing mass, a ghostly presence revealed only by its gravitational grip. We see its signature everywhere we look in the cosmos, from the way individual galaxies spin to the way entire clusters of galaxies move. A spiral galaxy, for instance, should rotate like a merry-go-round, with stars on the outer edges moving much slower than those near the center. But observations show something completely different. Stars on the galactic outskirts whip around at nearly the same speed as those close in. The only way this makes sense is if the galaxy is embedded within a massive, invisible halo of something, a substance that provides the extra gravity to keep those fast-moving stars from flying off into intergalactic space. This unseen matter is not just a small component. It makes up about 27% of the entire universe, outweighing all the normal matter, all the stars and planets and gas clouds we can see, by a factor of more than 5 to 1. So what is this invisible cosmic scaffolding? The leading candidates are exotic particles that barely interact with normal matter. One possibility is WIMP, or weakly interacting massive particles. These are theoretical heavy particles that would only be affected by gravity and the weak nuclear force, allowing them to pass through our planet as if it were not even there. Another candidate is the action, a particle that is incredibly light, but could exist in such vast numbers that its collective mass would be staggering. The challenge of finding these particles is immense. Scientists have built exquisitely sensitive detectors deep underground, shielded from cosmic rays, hoping to catch the rare, faint ping of a dark matter particle colliding with an atom of normal matter. Others search for indirect signals, like the unique light that might be produced if two dark matter particles were to annihilate each other in the emptiness of space. After decades of searching, we have yet to make a definitive detection. This invisible substance shapes the entire cosmic landscape, yet it remains frustratingly, profoundly out of reach. We are surrounded by an ocean of something we cannot see, cannot touch, and cannot explain, a fundamental component of reality that is completely hidden from our senses. The same dark matter that sculpts galaxies also carves out vast, haunting deserts in space. These are the cosmic voids, regions of stunning emptiness that stretch for hundreds of millions of light years. They are not just gaps between galaxies, but profound structural features of the universe itself, the inverse image of the bright, dense clusters and filaments. If the cosmos is a great cosmic web, then the voids are the immense, dark rooms in that web's architecture. Their existence presents a deep mystery. How did such enormous regions become so empty? And what do these great absences tell us about the forces that shaped everything? The story begins with the subtle ripples in the early universe, tiny variations in density imprinted on the cosmic microwave background. Over billions of years, gravity acted like a sculptor, relentlessly pulling matter toward these slightly denser spots. As matter flowed into what would become galaxy clusters and superclusters, it had to come from somewhere. The voids are that somewhere. They are the regions that were drained, the low-density troughs from which the universe's contents steadily flowed away. This process creates a universe of staggering contrast. Picture a sponge. The solid parts of the sponge are the dense filaments and clusters, packed with galaxies. The holes in the sponge are the voids, vast volumes of near-nothingness. In some of the largest voids, you could travel for the entire lifespan of a civilization and not encounter a single major galaxy. They are the quietest, most isolated places in existence. But these voids are not completely empty. They contain a sparse population of isolated, lonely galaxies, and they are filled with the mysterious dark matter and dark energy that permeate all of space. The very existence and size of these voids challenge our models of cosmic evolution. Their scale seems almost too perfect, their emptiness too profound. They are a fossil record of the universe's expansion and the tug-of-war between gravity and dark energy. By studying the geometry of these great nothings, we are essentially taking the universe's temperature, probing the fundamental laws that govern the growth of structure from the faintest whisper of sound in the newborn cosmos. Deep within the faint whisper of the universe's first light, a pattern emerges that seems to defy the very principle of cosmic uniformity. This is the mystery known as the axis of evil, a peculiar and controversial alignment found in the cosmic microwave background. The data reveals something profoundly strange. The hot and cold spots in this ancient radiation, the infant universe's fingerprint, are not scattered completely at random across the sky. Instead, they appear to show a subtle alignment along a particular plane, a kind of cosmic equator, with one half of the sky seeming slightly different from the other. This apparent axis roughly aligns with the plane of our own solar system, a correlation that makes physicists deeply uncomfortable. According to our fundamental cosmological principle, the universe should be largely the same in all directions, with no special place or axis. There should be no up or down, no left or right, on the grandest of scales. The discovery of a potential axis feels like finding a hidden compass painted on the ceiling of reality, pointing in a direction that, by all rights, should not exist. The debate over this anomaly is fierce. Many scientists argue it is simply a statistical fluke, a trick of the data or an artifact of how we have processed the immense amount of information from satellites like Planck and WMAP. They point out that when you look at any complex set of data, you can sometimes find patterns that seem significant purely by chance. It is like seeing a face in the clouds. The pattern is there, but it does not mean the clouds intentionally formed a face. Skeptics believe that with more precise future measurements, this apparent axis will simply fade into the noise. Yet other researchers are not so quick to dismiss it. They argue the signal is too persistent to ignore. If this axis is real and not an illusion, it would force a radical rewrite of our cosmic story. It could be a fossil imprint from a time before the Big Bang, a scar left on our universe from a collision with another universe in the multiverse. It might even suggest that the fundamental constants of nature are not the same in all directions, but vary subtly across space, guided by this hidden axis. The axis of evil confronts us with a haunting possibility. Is the cosmos truly isotropic and uniform, or are we living in a universe with a secret, fundamental direction? A cosmic north that challenges everything we thought we knew. This growing crisis in cosmology has a name: the Hubble tension. It is a stubborn and growing discrepancy that strikes at the very heart of our ability to measure the cosmos. The problem is deceptively simple. We have two primary ways to measure how fast the universe is expanding today: a number known as the Hubble constant. One method looks at the local modern universe. Astronomers use pulsating stars called Cepheid variables and cataclysmic stellar explosions, known as Type 1a supernova, as cosmic yardsticks. By carefully measuring their intrinsic brightness and their observed distance, they can calculate how quickly the fabric of space is stretching around us. This local measurement gives us one specific, precise number for the expansion rate. The other method looks back to the infant universe, using the cosmic microwave background. By analyzing the subtle patterns in this ancient light, scientists can use our well-tested theory of cosmic evolution to predict what the expansion rate should be today. This early universe method provides another very precise number. The crisis is this: these two numbers do not match. They disagree by a significant and persistent margin. It is not a small error that can be brushed aside. It is as if you used two different kinds of clocks to time a race. One clock, built with the latest technology, says the runner finished in 10 seconds flat. The other clock, designed based on the fundamental laws of physics, insists the race took 9.5 seconds. Both clocks are exquisitely calibrated, and both are considered reliable, yet they give irreconcilable answers. For years, astronomers hoped the discrepancy would vanish with more data, but the opposite has happened. With each new, more precise observation, the tension has only grown tighter. This is not just a minor accounting error in the cosmos. It suggests that something fundamental is missing from our picture of the universe. Perhaps our understanding of the early universe, based on the cosmic microwave background, is flawed in some subtle way. Or maybe dark energy is not constant as we assume, but is changing over time, throwing off our measurements. There is even the thrilling possibility that this tension is our first observational hint of an entirely new type of particle or force field that operated in the early cosmos and has left a permanent imprint on the expansion rate. The Hubble tension is more than a puzzle. It is a potential gateway. If it holds, it could force us to rewrite the textbooks and discover a new chapter in the laws of physics. This stubborn tension in our cosmic measurements echoes a far deeper and more fundamental imbalance written into the very substance of reality. Why is there anything here at all? According to the laws of physics as we understand them, the Big Bang should have created equal amounts of matter and antimatter. For every particle of matter, a mirror image particle of antimatter should have been born. The problem is, matter and antimatter are locked in a relationship of mutual annihilation. When a particle meets its antiparticle, they both vanish in a flash of pure energy. If the universe had begun in perfect balance, all of its contents should have annihilated shortly after its birth, leaving behind a cosmos filled with nothing but radiation, a sterile sea of light with no stars, no planets, and no one to wonder about it. The fact that we exist, that galaxies and planets and human beings are made of matter, is proof that this perfect symmetry was broken. Somehow, for every billion pairs of matter and antimatter that annihilated in the early universe, a single solitary particle of matter was left over. That 1 in a billion survivor is the origin of every single thing we see in the cosmos today. This is the mystery of baryon asymmetry, and its solution lies in a process called baryogenesis. Physicists have determined that 3 specific conditions had to be met for this tiny excess of matter to emerge. First, the early universe had to violate a fundamental symmetry of nature, a rule called baryon number conservation. This is the principle that the total amount of matter in the universe should stay constant. Somehow, this rule had to be broken, allowing matter to be created from energy without an equal creation of antimatter. Second, the interactions responsible had to treat matter and antimatter slightly differently, a phenomenon known as CP violation. Think of it like a coin that is not perfectly symmetrical. If you flip a perfectly symmetrical coin, you have an equal chance of getting heads or tails. But if the coin is weighted, even slightly, the odds are no longer 50-50. CP violation is that cosmic weighting, a tiny bias in the laws of physics that favors the production of matter over antimatter. Third, these processes had to occur out of thermal equilibrium, meaning they happened while the universe was changing so rapidly that the system could not settle back into a balanced state. It is like quickly freezing a liquid before its ingredients can separate. Scientists have observed CP violation in the lab, but the effect is far too weak to account for the vast amount of matter we see in the universe. This tells us that the CP violation we have found is just a small piece of a much larger puzzle. The leading theories for what caused the full baryogenesis event are some of the most ambitious in all of physics. They involve grand unified theories, which propose that 3 of the fundamental forces were once a single, unified force in the extreme heat of the early cosmos. As the universe cooled and this unified force split apart, it could have triggered the processes that generated the matter surplus. Other ideas point to the physics of neutrinos, those ghostly particles that barely interact with anything. If neutrinos are their own antiparticles, a special type of particle known as a Majorana fermion, then their unique interactions could have tipped the scales. The search for the answer is a hunt for the original, 1 in a billion event, the single, broken symmetry that made our material universe possible. Without it, reality would be a featureless, eternal glow, silent and empty. That 1 in a billion surplus of matter is not the only cosmic asymmetry born from the furnace of the early universe. Another profound absence haunts our theories, a missing particle that should be everywhere, yet we have never found a single one. This is the mystery of the magnetic monopole. Every magnet you have ever held, from a simple refrigerator magnet to the compass in your pocket, has two poles, a north and a south. If you break a magnet in half, you do not get isolated north and south poles. Instead, you create two smaller magnets, each with its own north and south. This is a fundamental feature of electromagnetism as we understand it. Electric charges can exist in isolation, a single positive proton or a single negative electron, but magnetic poles always come in pairs. Yet our most ambitious theories of physics insist this was not always the case. Grand unified theories, which describe how three of the fundamental forces were once a single, unified force in the extreme energy of the early cosmos, predict the creation of a staggering number of magnetic monopoles. These would be particles that are pure north or pure south, a single magnetic charge wandering through the universe. According to these elegant and powerful theories, these exotic particles should have been forged in unimaginable numbers in the first moments after the Big Bang. They should be stable, virtually indestructible, and should still be with us today, a common relic as widespread as photons or neutrinos. You should be able to hold a detector and find them zipping through your room right now. The problem is, we have looked. We have built sophisticated experiments, scanned the cosmos, and searched in moon rocks and deep underground. We have never, ever found a single confirmed magnetic monopole. Their total absence is a glaring contradiction, a ghost in the machinery of our most cherished theories. So where did they all go? The most compelling solution is the same cosmic event that solved the horizon and flatness problems: inflation. The theory proposes that the same violent, faster-than-light stretching of space that smoothed out the universe also diluted the monopoles to near nothingness. Before inflation, the universe was a dense, hot soup teeming with these theoretical particles. But when space expanded exponentially, doubling in size again and again in a fraction of a second, the density of monopoles was stretched to an almost infinitesimal level. It is like taking a single drop of ink and diluting it into an entire ocean. The ink molecules are still there, somewhere, but finding a single one in any given bucket of water becomes virtually impossible. Inflation scattered the monopoles so thinly across the vastness of the cosmos that the chance of one ever passing through our solar system is astronomically small. This solution is elegant, but it leaves us with a profound question. Is the emptiness we see, the absence of these predicted particles, actually the strongest indirect evidence for the violent birth pangs of our universe? We may be living in a cosmos that was once filled with wonders we can now only theorize about. Their traces stretched so thin by the fury of creation that they have vanished from our sight forever. This cosmic absence extends beyond monopoles and into the very substance we are made of. While dark matter and dark energy dominate the cosmos, the ordinary matter of stars, planets, and people seems to be only partially accounted for. This is the puzzle of the missing baryons. According to the highly successful theory of Big Bang nucleosynthesis, which accurately predicts the abundances of the lightest elements, we know precisely how much ordinary, or baryonic, matter the universe should have been born with. Yet, when we add up all the matter, we can see every galaxy, every star, every gas cloud. We only find about half of what our theories insist must be there. An enormous portion of the universe's normal matter has simply vanished from our view. So where did it go? The leading suspect is not some exotic, invisible particle, but familiar atoms hiding in plain sight. Scientists now believe the missing matter is scattered throughout the vast, empty spaces between galaxies, in a diffuse and incredibly hot web of gas known as the Warm Hot Intergalactic Medium, or WIM. This is not a cold, empty void, but a seething, invisible ocean of million-degree plasma, so thin that it is virtually impossible to see directly. Its individual atoms are so spread out and so energetic that they emit very little light, allowing this colossal reservoir of matter to remain almost perfectly camouflaged against the dark backdrop of space. How do you find something that is both incredibly hot and nearly invisible? Astronomers have developed clever methods to hunt for this ghostly material. They search for distant, brilliant objects called quasars, which act like cosmic lighthouses. As the light from a quasar travels billions of light years to reach us, it passes through these invisible filaments of the WIM. The highly ionized atoms in the gas, like oxygen and neon, absorb very specific wavelengths of this background light, leaving faint, telltale fingerprints in the quasar's spectrum. It is like detecting a specific gas in the air by analyzing how it dims the light from a faraway street lamp. By finding these absorption lines, scientists can confirm the presence and composition of this elusive matter. Another technique involves looking for the subtle shadows these filaments cast on the cosmic microwave background, the universe's oldest light. The hot electrons in the WIM scatter the SIMB photons, creating a faint, blurry patch in an otherwise pristine image. Piecing together this evidence, astronomers are slowly building a map of the cosmic web in all its glory, not just the bright nodes of galaxies, but the dark, flowing rivers of hot gas that connect them. This discovery completes our inventory of the normal universe, revealing that the missing half of all ordinary matter was not lost, but was simply hiding in the most desolate and unexpected of places, the great voids between the islands of light. Our universe contains more stars than there are grains of sand on every beach on Earth. With so many worlds, the silence from the cosmos is deafening. This is the heart of the Fermi paradox, a mystery that connects the sheer scale of reality directly to our own profound loneliness. If the universe is so vast and so old, then where is everybody? The numbers seem to promise a cosmos teeming with life. There are hundreds of billions of galaxies, each with hundreds of billions of stars. A significant fraction of those stars are likely orbited by planets in the habitable zone, where conditions could be right for liquid water and, perhaps, biology. Given these staggering odds, the galaxy should be a bustling metropolis of civilizations, with interstellar travelers and ancient, powerful empires whose presence would be impossible to miss. Yet, when we point our radio telescopes to the sky, we hear nothing but a background hum of natural static. The cosmos is eerily, mysteriously quiet. One straightforward explanation is the very vastness we have been exploring. The distances between stars are so immense that they create a kind of quarantine. Even if a civilization were broadcasting its existence from a nearby star, the signal would take years to reach us, and a two-way conversation would span generations. The sheer scale of space may simply isolate every emerging intelligence, trapping them in their own celestial islands with oceans of emptiness between them. But many thinkers find this answer unsatisfying. They propose a more unsettling possibility known as the Great Filter. This idea suggests that there is at least one nearly insurmountable barrier that prevents life from progressing to the stage of interstellar colonization and communication. This filter could lie in our past. Perhaps the emergence of life itself from non-living chemistry is astronomically rare. Or maybe the leap from simple single-celled organisms to complex, multicellular animals is the true bottleneck. If this is the case, then we are incredibly lucky to have made it through, and we might truly be alone in our galaxy. The more terrifying prospect is that the great filter lies in our future. There could be a recurring catastrophe that inevitably destroys intelligent species before they can spread beyond their home world. This could be a built-in self-destruct mechanism, like nuclear war, a bioengineered plague, or an AI takeover. Or it could be an external threat, like a gamma-ray burst that sterilizes planets on a regular basis. If the filter is ahead of us, then our current technological adolescence may be the calm before a storm that no civilization survives. The silence from the cosmos could then be a grim warning, a forecast of our own impending extinction. Every empty signal we receive asks us the same chilling question. Are we the first to make it this far? Or are we simply the next in a long line of civilizations that briefly flickered before being permanently snuffed out? The profound silence of the cosmos might have a staggering explanation, one that redefines the very meaning of reality. What if our universe is not the entirety of existence, but merely one page in an infinite cosmic library? This is the concept of the multiverse, a speculative but compelling idea that what we call the universe is just one member of a vast, perhaps infinite, ensemble of universes. The evidence for this is indirect, but it emerges naturally from our most advanced theories of physics. The first and perhaps most popular theory comes from cosmic inflation. We already discussed how a tiny patch of space underwent a violent, exponential expansion to become our entire observable cosmos. Eternal inflation suggests this process never truly stopped. While inflation ended in our patch, creating our Big Bang, it continues forever in the wider background of reality. Think of a vast, bubbling pot of water that is constantly boiling. Our universe is like a single bubble that formed, expanded, and cooled. But outside our bubble, the boiling continues, endlessly spawning new, separate bubble universes, each with its own Big Bang and its own unique properties. This creates a chaotic, infinite multiverse, a frothing sea of cosmic islands forever out of reach. A second theory arises from string theory, a leading candidate for a theory of everything. String theory proposes that the fundamental building blocks of reality are tiny, vibrating strings. To make the math work, string theory requires extra spatial dimensions beyond the three we experience. These extra dimensions are thought to be curled up into a complex, microscopic shape. The shocking discovery was that there is not just one possible shape, but a colossal number of them, perhaps 10 to the 500 different possible configurations. Each distinct shape would define a different set of physical laws and constants for its universe. In this string theory landscape, our universe is just one possible valley, one specific solution among an almost endless array of possibilities. The final major idea comes not from cosmology, but from the bizarre world of quantum mechanics. The many worlds interpretation proposes that every time a quantum event has multiple possible outcomes, the entire universe splits to accommodate each one. In this view, there is no single collapse of a probability wave. Instead, all possibilities are realized, but in separate, branching universes. In one universe, a radioactive atom decays, and in another, it does not. In one universe, you turned left on your way to work, and in another, you turned right, creating a new timeline that splits off and exists independently. This implies a constantly fracturing multiverse of staggering proportions, where every possible history and future is played out somewhere. The implications of any of these multiverse theories are profound. They could provide a stunning answer to the question of why our universe seems so finely tuned for life. If there are an infinite number of universes, each with different physical constants, then it is no surprise we find ourselves in one of the rare Goldilocks universes where conditions are just right for stars, planets, and life to form. We are not special, we are just lucky. The multiverse transforms the question of fine-tuning from a profound mystery into a simple matter of probability in an infinite ensemble. Yet this idea also confronts us with a deep philosophical challenge. If these other universes are forever causally disconnected from our own, can they ever be considered real in a scientific sense? Or does the multiverse remain an untestable, almost metaphysical idea? The search is on for any possible imprint our cosmic neighbors might have left on our universe, a faint scar from a long-ago collision in the primordial froth of creation. That ultimate horizon of time confronts us with the most profound edge of all, the beginning of everything. The Big Bang Theory describes a universe that has been expanding and cooling for 13.8 billion years. But if we run the cosmic film backward, we see all matter and energy compressed into an infinitely hot, infinitely dense point, a singularity. At this moment, the very concepts of space and time as we know them cease to have any meaning. Our entire framework of physics, the equations of general relativity that so beautifully describe the cosmos, shatters into nonsense. You cannot have a point of infinite density because infinity is not a number. It is a concept that breaks our calculators. This singularity is the ultimate barrier, a wall in time beyond which our science cannot see. So what, if anything, came before the Big Bang? The question itself may be flawed, because time, as part of the fabric of spacetime, may have been created in that initial event. Asking what came before the Big Bang could be like asking what is north of the North Pole. To penetrate this mystery, we need a new kind of physics, a theory that can unite the colossal gravity of the cosmos with the spooky, probabilistic world of the very small. This sought-after theory of quantum gravity would describe the universe when it was smaller than an atom, a realm where the smooth geometry of spacetime dissolves into a foaming, chaotic sea of potentiality. One of the most compelling ideas to emerge from this quest is the no-boundary proposal, developed by Stephen Hawking and James Hartle. It suggests that if we could travel back to the moment of creation, we would not find a sharp, singular point, but a smooth, rounded-off geometry. Imagine the very beginning not as a point, but as the rounded tip of a shuttlecock. In this model, the dimension of time behaves like a direction in space as we approach the beginning. There is no hard edge, no boundary, and therefore no need for a before. The universe would simply pop into existence from nothing, not with a bang, but with a smooth, quantum mechanical wobble. This leads to the staggering possibility that the question of what came before the Big Bang is rendered meaningless, because time, as we experience it, did not exist in that state. The universe did not emerge into a pre-existing void, but rather space and time themselves were born in that initial transition. Other theories venture even further, proposing that our Big Bang was not a unique beginning, but a cyclical event in an eternal cosmos, or the result of a collision between higher dimensional membranes in a bulk of reality we cannot perceive. Each of these ideas is a testament to our relentless drive to push past the ultimate edge, to gaze into the void from which we came and ask the final, unanswerable question. The smooth geometry of the Big Bang is mirrored by another cosmic edge that devours information entirely. Black holes present a paradox so deep it threatens to unravel our understanding of reality itself. At the boundary of a black hole, its event horizon, lies a point of no return. Once matter or light crosses this invisible threshold, it is lost forever to the outside universe, pulled by a gravitational grip so strong that not even light can escape. For decades, this was a straightforward, if terrifying, idea. Things fall in and they are gone. But then Stephen Hawking made a revolutionary discovery. He realized that black holes are not completely black. Due to bizarre quantum effects occurring right at the event horizon, they slowly leak a faint glow of radiation. This Hawking radiation is created when a pair of virtual particles pops into existence from the energy of the quantum vacuum. Normally, these particle-antiparticle pairs annihilate each other almost instantly. But at the very edge of a black hole, one particle can fall in while the other escapes, becoming real. The escaped particle carries away a tiny bit of the black hole's energy, causing the black hole to slowly lose mass and, over eons, evaporate completely. This creates a catastrophic conflict between our two most successful theories of physics: general relativity, which governs gravity and the large-scale universe, insists that the event horizon is a one-way street. Anything that crosses it is irretrievably lost, its information scrambled and destroyed beyond recovery. Quantum mechanics, the rules of the very small, has a fundamental, unbreakable law. Information cannot be destroyed. It can be scrambled, hidden, or transformed, but it must be preserved. You can burn a book, turning its pages to ash and smoke, but in principle, if you could collect every single atom and photon from the fire and trace their paths backward, you could reconstruct the entire book. The information is still in the universe. Hawking's calculations suggested that when a black hole evaporates, it leaves behind only a featureless cloud of thermal radiation. All the unique information about what fell in, whether it was a star, a planet, or a library of encyclopedias, is permanently erased from reality. This is the information paradox. The slow evaporation of a black hole seems to be the only process in the universe that fundamentally destroys information, violating a core principle of quantum theory. This is not a minor technicality. It strikes at the heart of whether the universe is predictable and lawful at its most fundamental level. If information can be lost, then the past is not determined, and causality itself breaks down. Physicists have been wrestling with this for decades, and potential solutions are as strange as the paradox itself. One idea is that the information is not actually lost. It is somehow encoded on the event horizon itself, like a cosmic hologram. As matter falls in, it leaves an imprint on the surface of the black hole, and this information is slowly and chaotically released in the Hawking radiation. Another, more radical suggestion is that there is no such thing as an event horizon in the way we think. Perhaps there is a fiery wall just inside the boundary that instantly incinerates anything that comes into contact with it, preserving information by never letting it truly enter the black hole. The truth remains elusive, a battle of titanic theories playing out at the edge of a gravitational abyss, forcing us to ask what truly happens to reality when it is stretched to its absolute limit. Those black holes, with their paradoxical evaporation, may have been pointing toward a deeper truth about reality all along. This leads to a mystery that is perhaps the most radical reimagining of our place in the cosmos: the holographic principle. The idea is as simple as it is bizarre. Everything we perceive in our three-dimensional world, from the stars in the sky to the very feeling of your own body, might be a projection. It could be a hologram, a three-dimensional image encoded on a distant, two-dimensional surface that surrounds us. The genesis of this principle comes directly from the black hole information paradox. When physicists struggled to understand how information could be preserved as a black hole evaporates, they made a startling calculation. They found that all the information about everything that ever fell into a black hole could be entirely encoded on its two-dimensional event horizon, the surface of its point of no return. The three-dimensional interior, with all its complexity, could be completely described by the information painted onto its two-dimensional boundary. It is like a DVD. A DVD is a flat, two-dimensional disc, but it contains all the information needed to project a rich, three-dimensional movie onto your screen. The holographic principle takes this black hole revelation and applies it to the entire universe. If a region of space can have its entire physical content described by information on its boundary, then perhaps our entire cosmos operates on the same rules. In this view, the universe we live in is the projected movie. The real data, the master disk, exists on a vast, spherical shell at the absolute edge of our observable universe. Every particle, every force, every event that we experience is just a translation of information stored on that remote, two-dimensional surface. This is not a metaphor. It is a serious proposal emerging from the mathematics of string theory and quantum gravity. It suggests that spacetime itself is not fundamental, but emergent. The smooth, continuous fabric of the cosmos we take for granted might be a secondary effect, a kind of illusion generated by the complex interactions of quantum bits of information living on that distant cosmic screen. Your perception of depth, of distance, of moving through a three-dimensional world would be a magnificent and convincing illusion. The universe is not a place, but a process. It is a computation. This principle resolves the information paradox by suggesting that information never actually falls into a black hole in the way we think. It is smeared and stored on the event horizon, and only appears to have a three-dimensional interior from our perspective. How could we ever test such an outrageous idea? Scientists are looking for subtle signatures in the cosmic microwave background, tiny imprints in the universe's first light that might reveal a pixelated, holographic structure to reality. They are also running simulations to see if the laws of physics, as we know them, can indeed emerge from a lower dimensional system. The holographic principle forces us to confront a humbling possibility. The solid, tangible reality we experience every day might be the grandest illusion of all, a spectacular shadow show cast from the edge of existence. This staggering vision of the multiverse introduces a profound and deeply puzzling question about probability itself. If an infinite number of universes exist, each with different physical laws, then everything that can happen does happen somewhere. This sounds like a straightforward answer to why our universe is so finely tuned for life. But this infinite variety creates a mathematical nightmare known as the measure problem. How do you calculate the odds of anything in an infinite cosmos? Imagine you are standing in an endless library that contains every book that has ever been written, and every book that could ever be written. You want to know the probability of randomly pulling out a science fiction novel. In a finite library, you could simply count the sci-fi books and divide by the total number of books. But in an infinite library, there are an infinite number of science fiction novels, and also an infinite number of romance novels, cookbooks, and volumes of complete gibberish. Infinity divided by infinity is not a number. It is undefined. So is the probability of finding a sci-fi book 50%, or 1%, or 99%. In an infinite set, all these answers are equally valid, which means no answer makes any sense. This is the core of the measure problem in cosmology. We need a way to cut the infinite multiverse down to size, to find a sensible method for counting or weighing the different types of universes. Without such a measure, the multiverse theory loses its predictive power. It cannot explain why we observe one set of physical constants instead of another, because in an infinite ensemble, every possible set of constants exists in an infinite number of universes. We are left with no reason for our own existence. Some regions of the multiverse might be far more prolific at producing bubble universes than others. A measure would tell us if we are typical residents of the multiverse or incredibly rare cosmic outliers. Are we living in a common type of universe, or did we just get lucky in an infinite lottery where every ticket is a winner? This is not just an abstract puzzle for philosophers. It is a crucial roadblock for making the multiverse a scientific theory. If we cannot define a probability measure, we cannot test the idea. We cannot say whether our universe's properties are likely or absurdly unlikely. The silence of the cosmos, the constants of nature, even our own existence, become meaningless statistics in an infinite sea of possibility. The search for a solution is a search for meaning itself, a way to find our footing in a reality without edges. Such precision in the cosmos points toward a mystery that strikes at the very heart of existence. Why do the fundamental numbers of the universe seem so perfectly set for life? The force of gravity, the strength of the nuclear forces, the mass of an electron, each of these constants has a specific value that appears to be exquisitely fine-tuned. If any one of them were altered by even a tiny fraction, the universe as we know it would be impossible. Imagine the strength of the force that binds atomic nuclei together. If it were just a few percent stronger, all the hydrogen in the early universe would have fused into helium almost instantly. There would be no long-lived stars like our sun, no stable solar systems, and no water. If that nuclear force were slightly weaker, heavy elements like carbon and oxygen, the very building blocks of life, would never form. Stars would be unable to cook these essential ingredients in their cores, and the cosmos would be filled with nothing but hydrogen. The same delicate balance applies to the force of gravity. If gravity were a little bit stronger, the universe would have collapsed back on itself in a fiery big crunch shortly after it began. If it were a little weaker, matter would have flown apart so quickly that galaxies and stars could never have coalesced from the primordial gas. We exist in a razor-thin window of viability, a cosmic sweet spot where the numbers align to allow for planets, chemistry, and ultimately, observers. This apparent fine-tuning leads to a profound question. Is this perfection a mere coincidence, a staggering piece of luck? Or does it point toward a deeper explanation for why the universe is the way it is? One of the most debated answers is the anthropic principle. In its simplest form, it states that we observe a universe compatible with our existence because, well, we are here to observe it. If the constants were any different, there would be no one to wonder about them. It is like a puddle of water marveling at how perfectly the hole it sits in fits its shape. The puddle does not realize that it is the hole that defines the puddle, not the other way around. In a multiverse of infinite universes, each with randomly dialed constants, it is no surprise that we find ourselves in one of the rare habitable ones. Our presence selects for the very conditions we observe. Another, more controversial, explanation is that of intelligent design, the idea that a cosmic architect set the dials intentionally. For some, the uncanny precision is evidence of a creator who established the laws of physics with life in mind. Scientists, however, generally seek naturalistic explanations, and the multiverse provides a powerful, if speculative, alternative. It turns a miracle into a matter of statistics. With an infinite number of cosmic dice rolls, every possible combination of constants will appear somewhere. We are simply living in the role that produced us, yet this answer leaves a haunting unease. Are we the beneficiaries of unimaginable luck, or just one outcome in an infinite cosmic lottery where every ticket gets drawn? The fine-tuning of the universe remains one of the most compelling and deeply philosophical puzzles, forcing us to confront whether our reality is a product of chance, necessity, or something beyond our current understanding. This fine-tuning of the cosmos hints at a reality even more strange, where the very flow of time is an illusion. Our next mystery asks if time itself is a fundamental ingredient of the universe, or merely a surface-level phenomenon that emerges from a deeper, timeless foundation. This idea comes directly from our attempts to unite general relativity with quantum mechanics, a quest that often points toward a reality where time, as we experience it, does not exist at the most fundamental level. In the equations of some leading candidates for a theory of quantum gravity, the variable for time simply drops out. The underlying description is of static, unchanging relationships. Think of the universe not as a movie with a clear beginning, middle, and end, but as a single, frozen frame. Our conscious passage from one moment to the next, the relentless tick of the clock, would then be a kind of collective hallucination, a story our brains tell us to make sense of this eternal snapshot. How could this be? One powerful analogy is temperature. Temperature is not a fundamental property of a substance. If you could look at a glass of water at the microscopic level, you would not see temperature anywhere. Instead, you would see a vast collection of water molecules jiggling and vibrating at different speeds. Temperature emerges from the average kinetic energy of all those frantic molecules. In the same way, some physicists propose that time emerges from the complex correlations and interactions between the fundamental quantum components of the universe. Our perception of a past, present, and future could be a similar statistical effect, a useful story that arises from a more basic, timeless network of connections. This has staggering implications for our understanding of cause and effect, the very bedrock of reality. If time is not fundamental, then the chain of causality, the idea that one event must always precede and cause another, begins to unravel. The universe would not be a series of dominoes falling in sequence. It would be a single, intricate pattern where all events, from the Big Bang to the distant future, are equally real and eternally present. The edge of the universe, both in space and time, would not be a boundary where things begin or end, but simply the limit of the pattern we can perceive. This forces us to reconsider the very notion of a beginning. Was there a first moment, or is the Big Bang just one particular feature of this timeless whole, a point where our emergent sense of time seems to start? The search for the edge of reality may ultimately lead us to a place where time itself dissolves, leaving us to wonder if our entire history is just one thread in an eternal, unchanging tapestry. The shape of the universe might be far stranger than a simple, infinite plane. While all our measurements point toward a flat geometry, that does not necessarily mean space goes on forever. A flat universe could still be finite if it is wrapped in on itself in a multiply-connected shape. The most famous example is the three-dimensional torus, which we can picture as a giant cosmic donut. In such a universe, if you could build a spacecraft powerful enough to fly in one perfectly straight direction, you would not journey into an endless void. Instead, after an extraordinarily long voyage, you would eventually return to your exact starting point from the opposite direction, having circumnavigated the entire cosmos without ever encountering an edge. It is a finite space without a boundary, a closed loop on an unimaginable scale. The key to detecting this bizarre topology lies in the oldest light we can see. The cosmic microwave background radiation is a fossilized snapshot of the universe when it was just an infant, and it carries imprints of the largest possible structures. If the cosmos is shaped like a torus, then space would wrap around, and the light from the Big Bang would have taken multiple paths to reach us. This would create matching patterns, like ghostly circles or pairs of identical cold spots, repeated across opposite sides of the sky. It would be as if you were inside a hall of mirrors, seeing the same reflections of the same objects from different angles. Astronomers have searched for these telltale correlations in the data, but so far, no definitive evidence has been found. The universe, on the largest scales we can measure, appears simply connected, yet the possibility remains tantalizing. A finite, toroidal universe would resolve the philosophical tension between a flat geometry and an endless reality. It would mean our entire cosmos is a self-contained system, a colossal but finite island where every point is ultimately connected to every other. The implications for a far future civilization are staggering. Instead of being lost forever in an infinite expanse, they could one day chart a course that loops through the whole of creation, mapping the entire cosmic donut and returning home to tell the tale. The largest structures in the cosmos, the great galactic filaments, and the immense voids between them, all trace their origin back to the smallest possible vibrations. The seeds for everything were sown in the first fleeting moments of time, born from the ghostly dance of quantum fluctuations. In the seething quantum foam of the newborn universe, pairs of virtual particles were constantly blinking in and out of existence, a temporary loan of energy from the vacuum itself. These were not true particles in the sense we understand, but momentary ripples in the underlying fields of reality, a fundamental fuzziness at the heart of everything. On their own, these quantum jitters were unimaginably small and fleeting, confined to a subatomic realm. But then came inflation, the violent, exponential stretching of space in that first fraction of a second acted like a cosmic amplifier. It grabbed these microscopic ripples and stretched them across the sky, freezing them into permanent imprints on the fabric of the cosmos. A tiny region that was ever so slightly more dense than its surroundings, due to a random quantum fluctuation, was inflated to a scale of hundreds of millions of light years. That slight overdensity became the gravitational seed for a future supercluster of galaxies. Conversely, a region that was a tiny bit emptier was stretched into one of the vast cosmic voids we observe today. This process created a specific, predictable pattern, a fingerprint of the early universe that we can still read today. The cosmic microwave background, that ancient light from the Big Bang, is not perfectly smooth. It is mottled with tiny variations in temperature, hot spots, and cold spots that correspond to those initial density variations. These minute differences, mere millionths of a degree, are the amplified echoes of quantum noise. They are the original blueprint, the cosmic recipe from which gravity would later sculpt every galaxy, star, and planet. This is the profound bridge between the quantum and the cosmic. The random, probabilistic rules that govern the behavior of a single electron are directly responsible for the grand architecture of the universe. The very existence of our Milky Way galaxy and our place within it can be traced back to a specific quantum fluctuation that happened over 13 billion years ago. Without these random seeds, the universe would have remained a featureless, uniform soup of particles, with no structure, no stars, and no one to contemplate its origins. The universe we see is not a preordained structure, but the magnificent and complex outcome of quantum chance, writ large across the heavens. Our own galaxy is not drifting aimlessly through the cosmos. The Milky Way, along with our entire local group of galaxies, is caught in a vast, mysterious river of motion, all flowing toward a single, unseen destination. This is the enigma of the Great Attractor, a colossal gravitational anomaly located in the depths of intergalactic space. Something with the mass of tens of thousands of Milky Way galaxies is pulling us, and thousands of other galaxies, toward it with immense force. We are moving at an incredible speed of over 2 million kilometers per hour toward a point in the constellation Centaurus, a relentless cosmic current we cannot resist. The identity of this gravitational titan remains one of the great cosmic detective stories. Our biggest challenge in solving it is our own galaxy, the plane of the Milky Way, thick with stars, gas, and dust, lies directly between us and the Great Attractor. This region is known to astronomers as the zone of avoidance, because it effectively blocks our view of the universe beyond. Trying to see through it is like trying to spot a distant mountain range through a dense, ground-level fog. The light from objects behind this zone is absorbed or scattered, rendering them nearly invisible to our optical telescopes. For decades, this cosmic blind spot hid the true nature of the Great Attractor. But scientists are a persistent bunch. They have turned to instruments that can see through the dust, using radio waves, X-rays, and infrared light to pierce the galactic veil. These new eyes have revealed that the Great Attractor is not a single, monstrous object, but likely the core of a gigantic supercluster of galaxies, an immense knot in the cosmic web where gravity has drawn together a staggering amount of mass. This structure, known as the Laniakea supercluster, is our home on the grandest scale, a vast filament of galaxies spanning over 500 million light-years, and the Great Attractor is its gravitational center of mass. Yet the mystery may go even deeper. There is evidence that the pull we feel might not stop with the Great Attractor itself. Our entire supercluster, including the Great Attractor, appears to be drifting towards something even larger and more distant, an inconceivably vast concentration of mass nicknamed the Shapley Attractor. This suggests a cosmic hierarchy of pulls, a river flowing into an ever larger ocean of gravity. The search continues to map this hidden geography, to understand what ultimate structures are guiding the motion of galaxies across the universe. We are like sailors on a vast, dark sea, feeling the pull of a hidden current, slowly charting the invisible forces that have been shaping our journey for billions of years. The light from the most distant quasars carries a strange and ghostly signature on its long journey to our telescopes. As this ancient light travels for billions of years through the vast emptiness between galaxies, it does not pass through a perfect void. Instead, it filters through a diffuse, cosmic fog of neutral hydrogen gas, the most basic building block of the universe. Each individual cloud of this primordial gas absorbs a very specific wavelength of the quasar's light, a fingerprint known as the Lyman alpha line. Because the universe is expanding, these gas clouds are all moving away from us at different speeds. This stretches the light, shifting the absorption lines to different positions in the spectrum. The result is a stunning pattern. Instead of a single, clean absorption line, the quasar's spectrum is carved up into a veritable forest of lines, each one representing a different cloud of hydrogen at a different distance along the line of sight. This is the Lyman Alpha Forest, a cosmic barcode imprinted on the most distant beacons in the cosmos. It is not a static picture. By analyzing the density and spacing of the lines in this forest, astronomers can read the history of the universe's structure. In the early universe, the forest is thick and dense, a jungle of absorption lines indicating that space was filled with a relatively smooth distribution of gas. As time passes and gravity works its magic, the forest begins to thin out in certain regions. The gas is pulled into the great filaments and knots of the cosmic web, clearing out vast tunnels along the lines of sight to distant quasars. This forest is therefore a living fossil record. It shows us the distribution of ordinary matter in the most desolate regions of space, the very material that would eventually flow into galaxies. It provides a unique three-dimensional map of the cosmic web itself, a map not of bright stars, but of the dark, flowing rivers of gas that connect them. By studying the intricate patterns in this ghostly forest, we are essentially taking core samples from the universe across billions of years, reading the story of how nothingness became something, and how the great cosmic structures we see today first began to form from a nearly invisible haze. The very particles screaming across the cosmos carry their own secret boundary, a theoretical speed limit for the universe's most energetic travelers. We call this the Gizike cutoff, a barrier not of space, but of energy. It is a limit predicted by physicists Greisen, Zatsepin, and Kuzmin, based on a simple, brutal principle. The space between galaxies is not completely empty. It is filled with the faint, cold glow of the cosmic microwave background, the relic radiation from the Big Bang. For a proton traveling at nearly the speed of light, with an impossibly high energy, this background radiation is not a gentle glow. It is a dense fog of high-energy photons. When such an ultra-high-energy cosmic ray collides with one of these cosmic microwave background photons, the interaction is catastrophic. It is like a bullet hitting a brick wall. The proton loses a tremendous amount of energy in the collision, producing a shower of other particles. According to our best models, this process should prevent any cosmic ray proton from traveling more than about 150 million light-years before its energy is sapped away below the cutoff point. This creates a cosmic horizon for these particles, similar to our light horizon. We should only be able to detect ultra-high-energy cosmic rays that originate from relatively nearby sources within our local cosmic neighborhood. The universe, it seems, has a built-in speed bump for its most energetic particles, yet our detectors on Earth have recorded a handful of events that defy this law. We have seen cosmic rays with energies so stupendously high that they should not exist, particles that have apparently traveled from distant realms and arrived with an energy that, by all rights, should have been stripped away by the cosmic microwave background long ago. It is as if a marathon runner arrived at the finish line not only unexhausted, but bursting with more energy than they started with. This presents a stark mystery. Either these particles did not come from far away, meaning there are incredibly powerful, unknown accelerators lurking disturbingly close to our own galaxy, or our understanding of how particles interact at these extreme energies is fundamentally flawed. What cosmic engines could possibly generate such ferocious power so nearby without us having identified them? Or are we witnessing the first cracks in the standard model of particle physics, a glimpse of new laws that only reveal themselves at energies we can scarcely recreate? These rare, enigmatic particles are messengers from the edge, challenging our maps of both the cosmos and the rules that govern it. That profound silence was broken just once, by a signal so powerful and strange it has never been forgotten. In 1977, a radio telescope in Ohio picked up a 72-second burst of radio waves so intense that the astronomer who found it, Jerry Amon, simply circled the data printout and wrote one word in the margin: "Wow." This was not random static. It was a strong, narrowband signal, precisely the kind we would expect from an artificial, interstellar broadcast. It came from a region of space in the constellation Sagittarius, and then, just as suddenly as it appeared, it vanished. Despite decades of repeated searches, the WOW signal was never heard again. It remains the single best candidate for a potential extraterrestrial transmission in the history of the search for alien intelligence. Its brief, brilliant flash is a perfect cosmic tease, a one-word question mark hanging in the void. The universe provides other fleeting enigmas. Astronomers now catalog events known as fast radio bursts, or FRB. These are blasts of radio energy that last for mere milliseconds. Yet in that flash, they can release more energy than our sun emits in 80 years. Most of these bursts are one-off events, but a few are repeaters, flashing from the same patch of sky again and again without any discernible pattern. We have theories about their origins, pointing to immensely powerful objects like magnetars, which are neutron stars with unimaginably strong magnetic fields. But the precise engine that can create such a short, sharp, and energetic crackle remains a topic of fierce debate. What makes these anomalies so deeply compelling is the context in which they occur. They are isolated shouts in an otherwise silent cosmos. For every one of these mysterious events, there are countless hours, years, and centuries of perfect, unbroken quiet. Our telescopes are constantly listening, and almost always, they hear nothing but the natural hum of the universe. It is this vast, empty backdrop that gives the rare anomaly its immense weight. A single, unexplained blip on a graph forces us to confront the ultimate question. Was it a natural, if exotic, cosmic event we do not yet understand? Or was it, for one breathtaking moment, a sign that we are not the only ones listening? The silence that follows is the most profound part of the message, leaving us to wonder if we just missed a call, or if the universe is simply reminding us of how much we have yet to learn. That profound silence could be the most important clue of all, pointing toward a paradox that questions the very nature of our own existence. The Boltzmann brain thought experiment presents a bizarre and unsettling possibility. In a universe that is either infinitely old or part of an infinite multiverse, the laws of probability begin to produce truly strange outcomes. Given enough time and space, even the most wildly improbable events are not just possible, they are inevitable. The spontaneous, random assembly of atoms is far more likely to produce a single, self-aware brain, complete with false memories of a past and a convincing sensory input of a world around it, than it is to produce an entire, coherent, and ordered cosmos spanning billions of years. The odds of a universe like ours forming through a long, slow process of stellar evolution and biological adaptation are astronomically small, but the odds of a single, conscious brain popping into existence from a chance quantum fluctuation in the void are, in an infinite reality, actually higher. This is the core of the paradox. If our standard cosmological models are correct, then the most likely explanation for your feeling of consciousness, right now, is not that you are a person living in a real universe. It is that you are a lone, disembodied brain that just randomly coalesced from the chaos. complete with the elaborate and entirely fictitious memory of reading this sentence. The universe you think you see around you would be nothing but an incredibly detailed hallucination, a brief flicker of false consciousness before the brain dissolves back into the formless void. This idea forces us to confront the most fundamental assumptions we hold. How can we trust our memories, our observations, and our scientific conclusions about the cosmos if the most probable state of existence is a solitary, self-deceiving mind adrift in nothingness? The Boltzmann brain paradox is not just a puzzle about cosmology. It is a profound challenge to our understanding of reality, probability, and the nature of consciousness itself. It suggests that our most basic experience of being in an ordered, lawful universe might be the ultimate statistical fluke, a temporary and unlikely glitch in an eternity of chaos. The silence we hear from the cosmos might not be the silence of empty space, but the silence of our own profound solitude in a reality where true, sustained order is the real impossibility. That unsettling thought experiment forces us to confront the most radical edge of reality mystery of all. Could our entire universe, with its 13.8 billion years of cosmic history, be nothing more than an elaborate simulation? This is not science fiction, but a serious philosophical argument with profound implications. Philosopher Nick Bostrom formalized this idea into a stark trilemma, a set of three possibilities, at least one of which must be true. The first possibility is that almost all civilizations at our level of technological development go extinct before they can create realistic simulations. The second is that any advanced civilization that does survive has no interest whatsoever in running ancestor simulations, perhaps for ethical or practical reasons. The third, and most startling, is that we are almost certainly living in a simulation right now. If even a single advanced civilization avoids extinction and develops a passion for creating simulated realities, they could generate a literally astronomical number of them. The number of simulated minds would vastly outnumber the one original biological population. Therefore, if such simulations are possible, the statistical odds are overwhelming that you and I are not in the original base reality, but in one of the countless simulations. The logic is as cold as it is compelling. This hypothesis finds a strange echo in the holographic principle we explored earlier. If our three-dimensional reality is actually a projection from a two-dimensional surface, is that not, in essence, a form of simulation? The universe would be operating like a cosmic computer, rendering our experience from a more fundamental layer of information. The laws of physics, with their discrete values and mathematical elegance, begin to look less like fundamental truths and more like the underlying code of a sophisticated program. So how could we ever test this? Some physicists suggest looking for glitches in the matrix, tiny errors or shortcuts in the simulation. Perhaps at the very smallest scales, spacetime reveals a pixelated structure, a fundamental resolution limit. Others propose that we might find evidence in the behavior of high-energy cosmic rays, which could expose approximations in the rendering of our reality. Even the strange results of the double-slit experiment in quantum mechanics, where particles seem to behave differently when observed, could be interpreted as a processing optimization, where the simulation only calculates precise details when someone is looking. Yet powerful arguments push back. The sheer computational power required to simulate every particle in a universe, let alone the consciousness of every being within it, is mind-boggling. Would any civilization, no matter how advanced, bother to simulate the entirety of cosmic history down to the last quark. Perhaps they would, or perhaps our level of detail is an illusion, and only the things we directly observe are fully rendered. Ultimately, the simulation hypothesis remains untestable with our current knowledge, a metaphysical hall of mirrors. It forces a humbling question onto us. If we cannot prove we are in a base reality, and if the statistical argument holds any weight, then where does that leave our search for truth? We are left to wonder if the final edge of the universe is not a boundary in space or time, but a firewall of pure information, and we are merely characters in a story whose author we can never meet. From the silent horizon of our observable universe to the echoing paradox of the Boltzmann brain, we have charted 30 of the cosmos's deepest puzzles. This journey has taken us from the quantum seeds of galaxies to the terrifying possibility that our reality is a hologram or a simulation. We have confronted the ghostly pull of dark matter, the enigmatic push of dark energy, and the profound silence that greets our search for other life. Each mystery, from the fine-tuning of physical constants to the missing magnetic monopoles, is not a dead end but a doorway. They are the unanswered questions that keep the engine of science running, pushing our species to look deeper, think harder, and reach further into the unknown. The true edge of the universe is not a place you can find on a map. It is the frontier of human understanding, a boundary that recedes with every new discovery, only to reveal even grander questions waiting in the dark. Now, the journey continues with you. Which of these 30 mysteries captures your imagination and keeps you staring at the stars? Share your thoughts in the comments below. And if you are ready for more voyages to the edge of reality, be sure to subscribe.